So last time we were just about ready to try a new algorithm for evaluating polynomials called Horner's method. So let's go ahead and scroll to that page. It should be on page 243, which is section 3.3 in the homework in the book. So let me just zoom in on it real quick. All right, then let me write this out. So Horner's method for evaluating polynomials looks like this. The variable y is assigned to equal the coefficient called an. And who remembers what an coefficient was the coefficient of? Remember how that in variable naming was defined as? An was always the coefficient of which power of x? Yeah, the nth power, right? Yes. So like a0 was the coefficient of the term that had no x. That's why it was called a0 because it had 0x beside it. A1 was the coefficient of x to the power of 1. A2 is the coefficient of x to the power of 2. And an was the coefficient of x to the power of n, which was the biggest one. Yep. So we start out with the coefficient of the biggest power of x, and then we start a loop. Now, remember, this is going to only have n operations to do. So that means that you can only have one line of code inside of the loop that goes from 1 through n. Okay, so that projector apparently did actually start working this morning. So do you still have the Zoom app installed on your phones or anything like that? Okay, see, I can't even turn it off even because it's like in some mode. So go ahead and get your Zoom app, and I will email you an invitation link. If you still have the email from before, you can try that one. Perfect. Okay, perfect. Okay, let's see here. What am I looking for? Emailing you guys a link, right? Okay, let me do that real quick. So participants, okay, hold on. How do I do this? Oh, there we go. Send email to Joseph Myers, friends.edu. Okay, there, I sent myself an email. And then once that email comes, I'll send it to you all. In fact, I'm just going to send it with Moodle so that in case anybody else gets here late, they can do it.
Maybe the projector was hungry.
Yeah. Right. Well, that teacher from the previous class told me last week that it stopped working for him. So I believe him, but sometimes it always doesn't do the same thing. So I guess it's just slowly failing, maybe. How many hours do you think that projector has shined before now? Like in all the years it's been running. Okay, let's see. Okay, the email still has not arrived. Come on, let's go. Let me make sure it actually sent. Don't allow. Sent. Okay, so it says it's sent. Okay, no, that still has not come. Okay, there, finally. Why does email go so slow? You'd think that it'd go faster. Do you guys have, would it be better for me to email you or to send it to you in a Moodle message? Would that go to your email too, right?
I think email's quicker.
Probably. Let me try Moodle message first, just because that way I can send everybody at once. So it might take a minute longer, but it might take a minute less for me to actually email it out. So let me just select you all. There we are. Send a message. Zoom class link. All right, it should have gotten sent. It might take a minute or so for it to arrive though. So, by the way, let me go back to attendance real quick. So LaShawn, you walked in. Oh, there's Zoe, perfect. And LaShawn and what's your name in the white shirt right there?
Matthew.
What?
Matthew.
Ignacio. Oh, hello. Are you here for the projector?
Well, yeah, I don't know what's wrong with it. It's only a year old, but I can bring over a projector real quick and set one
Well,
on the table here. for you.
Actually, I think everybody has the Zoom app installed, so I'm just using, I
Okay.
just sent them a Zoom link out. And by the way, how did you even hear about the issue?
How did I hear about it?
Yeah.
Oh, someone just give it a help desk ticket.
Oh, okay. So it must have been the person before me.
Yeah.
Yeah, because he was having issues with it last week, but it didn't happen for us. But then it happened for us the first time, like right now. So
Yeah. Well, I have a feeling I'm looking at this up here. There's 79% humidity in the room. I don't know if that has anything to do
oh
with it.
yeah, that could probably have
Well, I
something
won't
to do
interrupt
with
your
it.
class any longer, but we'll figure out
No,
something.
that's okay. That's okay. But thankfully, we have like an online ongoing class, so I'm already recording it
Okay, cool.
on Zoom. And so everybody has a Zoom app on their phones and they're just logging into Zoom.
All
to
right, very
watch.
good. Well, we'll figure out something. I don't
Thank you.
I don't have any more digital projectors, but I got something we can put up there.
Perfect.
So, all right.
Thank you very much. Okay, so Anthony, sorry, not Anthony, LaShawn, and then Ignacio, right? Ignacio. And is that it? That's just 5 people total. Okay, perfect. So Horner's methods, so can you all see this on your screens? Let me just make sure. Want to make sure everybody can see it.
It's still running on my end. Yeah. More company.
And you don't actually have to log into Zoom to watch it. You just have to have the Zoom app installed. That's all. And then once you click on the link in your email, then, or even the link in Moodle and the Moodle messages, either one, it'll bring it up. But I just want to make sure everybody's watching it before I keep going. Perfect. Okay, let me go ahead and accept you in. So view, admit all. So Ignacio, Arturo. So I have Arturo, Zoe, Ignacio. And then what about Colin?
Yeah. Where next to is.
Perfect. Okay, I got you, LaShawn. And then yours is starting.
Yeah.
Perfect. Okay, Colin, admit. There we go. What? Wait. Okay, there. It says you're in now. I had to click admit on like 2 different spaces for some reason. Okay. So everybody's in. 1, 2, 3, 4, 5. Okay, perfect. That's great. Now make sure you keep watching your screens and everything like that. I'm just to test if you're watching your screens, I might put like a secret code or something on the screen. And you should say like respond to it or whatever like that. So remember the green game I played one time? Colin, do you remember the green game I played one time? So like if I write like a green dot on the screen, then everybody needs to say green. To make sure that you're paying attention. Okay, so now Horner's method. Oh, I'm on it. Okay, perfect. So Horner's method says for I equals 1 to n, and it only has one statement after that, which is kind of like black magic, because how do you do it in only one statement? So notice so can everybody see that? Notice the strange thing, feels like you can't see it since the screen is blank, but I'm just trusting that you can see it. By the way, do you want me to turn on the lights again since you have it on your phones and you don't have to have the lights out? How's that? That way you can see to write better. So y equals an for I equals 1 to n, y equals c times y plus a of n minus I. So what exactly does that even do, or what does that mean? By the way, this is an optimal method. You can't actually evaluate a polynomial in less steps than this. There's no algorithm that can do it in general in less than n steps for an nth degree polynomial. So this is not necessarily the most numerical stable, though, because of how math works on computers. The most stable way to evaluate polynomials is when they're expressed as factors. So once again, that goes back to college algebra when I told you that factoring is really important. But if you don't express them as factors, this is one of the fastest in terms of computational steps to do. And how exactly does it work? Well, good morning. Let's go ahead and take a polynomial. And when you do the homework, you have to do the polynomial 3x squared plus x plus 1. So I'm going to change that a little bit. We're going to use this method right here to evaluate the polynomial. I'll just say 3x squared and then plus 2x plus 1. So 3x squared plus 2x plus 1 is what we're going to do instead of the one in the homework. But when you turn in your homework, though, you have to do these same steps with your problem. And we need to step through this algorithm showing every step that happens. So first of all, y is equal to an, which is a2, right? So y equals a2, what is a2? Can anybody tell me the value of a2? And by the way, I sent you a link to log in. Are you Logan? I sent you a link to log in, so let me make sure you can get logged in and join the meeting. Because the projector is not working today. Oh, okay. Yeah, I got it. Perfect. So let me make sure you can get logged in before I keep going. All right. As long as you have Zoom in your computer, all you have to do is just click the link and then they'll open Zoom up. Yeah, either one. Yeah, you can do it on your phone as well. Just I'll make sure that you get logged into the Zoom app because I can see who's going from the Zoom screen. There we go. Perfect. Okay. Admit. All right. So then y equals a2 because that's the value of n, right? And what is a2? 3. 3, correct. And the next step of the algorithm is a for loop. It says for I equals 1. So the value of I is going to be equal to 1, right? And by the way, that's called a bookkeeping step. And that's not part of the n steps of the algorithm in terms of evaluating the polynomial because that doesn't involve multiplying things in the polynomial together. So mathematically, that's not counted as one of the n steps, but it actually is one of the steps the computer has to do. So if there's a faster way of counting things up, instead of like counting from I equals 1 through n, that actually can make it go even faster. So I equals 1. The next step is y equals c. Okay, now I have to tell you what value of x to plug in. So I'm going to tell you to plug in x equals 3. So we're going to plug in x equals 3. So it says y equals c times y plus a of n minus I, which is 2 minus 1. So I'm writing down the numbers they're going to be used. And what's the value of c? Who remembers what the value of c is in this code? Correct. C represents the value that's being plugged in, the x value. So it's 3 times, and what's the value of y at this current moment? The previous value of y. 3. And what is a of 2 minus 1? Well, what is 2 minus 1? 1. And a1 is what's left. And what does a1 represent? Yep, correct. So 3 times 3 is 9, and a1 is the coefficient of x to the power of 1, which is 2. So you have 9 plus 2, which equals 11. So y equals 11. Then we're going to go through the loop again. So this loop is going to be repeated for the value of 2, because the loop runs for I equals 1 through n, which is going to be 1 through 2. Then the line of code inside the loop is going to run, which is y equals c times y plus a of 2 minus 2, which is going to be equal to c, which is 3, times y, which is 11, plus a0. And who knows what a0 represents? Correct. It's the a0 is the coefficient of the problem that has 0 x's beside it. So 3 times 11 is 33, plus 1, which is a0. What's 33 plus 1? 34. Now the loop ends at this moment. So this value of y is the final value of y. So this is going to get returned. I'm just going to say, in parentheses, returns a value of 34. That means that's the final value that the code returns as the result of the function, as a result of the algorithm. So let's check and see if 34 is really correct. What's the value of the polynomial if we do it with algebra? If we take 3x squared plus 2x plus 1 and we plug in 3, we get 3 times 3 squared plus 2 times 3 plus 1, which is 27, plus 6 plus 1, which is 33 plus 1, which is 34. So it calculated correctly the value of 34. And it only had to do 2 lines of code to do it with. So what are the 2 lines of code? The 2 lines of code that did it with are this line right here and this line right here. So when you write out your homework for this problem, you make sure you write it out just like this. You show everything that gets plugged in and so forth. Does that make sense? So let's go ahead back to question 21. I'm going to do something similar to that. So the last homework problem for that's due tonight is from the same section, question 21. And it says, what is the effect in time required to solve a problem when you increase the size of input from n to a size of n plus 1? So A, it says log. Okay, I'm going to have to change this a little bit. Kind of hard to change it though, because there's not really much to change. Log of n. How can I change that? I'm going to change it from log of n to be natural log of n instead. And then B, instead of being 100n, I'm going to change that to be 50n. So make sure you do it with 100n though. C, instead of being n squared, I'm going to change it to be, wow, it already has n cubed. I'll change C to be n cubed and D to be n squared. So you'll just have to do them backwards when you do it in your homework. And then E says 2 to the n. I'm going to change that to be 3 to the n. And then F, it says 2 to the n squared. I'm going to change that to be 3 to the n squared. And then G, it says n factorial. I'm just going to leave that one. What can I do to change that one? I'm gonna leave that one the same. I'll give you a freebie, okay? So it asks us what changes in how much time or how many calculations have to be computed when you work these algorithms on the input size of n versus n plus 1. You ready? So first of all, how much time does it take to do this algorithm when you have n data points to plug into the algorithm? And then how much time does it take for n plus 1 data points? Then we're going to divide those each by each other and figure out which one goes faster. So just a second. There's a Zoom link that I emailed out to you. So log into your email real quick and click on the Zoom link, and you make sure you're watching it on your phone. I'm going to wait till you've joined the meeting to keep it. Well, make sure you join it on your phone as well, though. So yeah, just to make sure I can keep track of you. Let's see. And you are by the way, you're Logan, right? Okay, perfect. Good job. And you're Isaac, is that right? Are you Isaac? Okay, Isaac, perfect. Perfect. So once you get logged in, I'm going to accept you real quick. But I will keep going though. But I'm going to wait until I check you in until you get joined in on Zoom. Okay, so time for n. Okay, there we go. Perfect. All right, great job. Okay, perfect. So how much time does it take for n steps? Actually, that's already written down. So unfortunately, I can't really point to it with like a yardstick, but the time it takes for n steps is actually already written down. So how much time does it take to do this algorithm for n steps? It's written down right there where I'm pointing to. Natural log of n, right? And so that one's actually already done. So let me actually erase that because I don't need to do that. That's already written down. So the time it takes for n steps is written down already to do n steps. So now I need to figure out how much time it takes to do for n plus 1 steps. All you have to do to calculate the amount of time it takes for n plus 1 steps is just substitute for the value of n, just substitute n plus 1. That was pretty easy, wasn't it? So how much time does it take to do n plus 1 steps? Natural log of n plus 1. And how much faster is it? Well, how much faster or slower? How much faster or slower? Well, how do you define how much faster or slower something is? Like if somebody runs slower than you, how do you define what that is? Time, right? And so like let's say if somebody takes twice as much time as you did, would it be better to express that as saying they took 1 second longer or twice as much longer or twice as long? Which would be a more clear statement, or does it depend on the situation? Probably depends, right? So let's just let's express this first one as a difference. So the time it takes to do the second amount of data is ln n plus 1, and the time it took to do the first amount of data is ln of n. So let's just subtract them. That's how much longer it takes. ln of n plus 1 minus ln of n, that's the additional amount of time. How big is that though? Let's look at Desmos.com real quick. Well, we can't really see Desmos.com on your window, but I'm just going to write down in just in a quick note though that this is actually going to be, as long as n is bigger than maybe like 2 or 3, this is going to be less than a 1 second difference. So that's ln of n plus 1 minus ln of n is going to be less than 1 second. In fact, as n gets bigger and bigger, like to 1,000,000 or whatever, that's going to be even a whole lot smaller than just 1. Now let's go to the next one. So if you have an algorithm that has a level of 50 n steps, how much time does that take? If it takes 50 n steps, how much time does it take to do the value of n operations? That's just actually a trick question because it's already written down. So the time it takes is 50n. How much time would it take that algorithm to do n plus 1 steps? 50 times n plus 1, right? That's pretty easy. So what's the difference in time between how long it takes to do the algorithm for n steps versus n plus 1 steps? What is 50 times n plus 1 minus 50 times n? What's the difference in time? What's the difference between 50 times n plus 1 minus 50 times n? 50 more steps. You're right, exactly. It'll have 50 more steps. So the difference in time is 50 seconds or 50 milliseconds or 50 units of time. However much time that it takes to do one basic step, it takes 50 of those steps, right? So it's basically takes 50 units of times more time to do the algorithm. What about n cubed? Well, so let's just check real quick. So how much time does it take does the algorithm take to calculate the output for a value of n data points, n plus n to the third power time amount of time, right? How much time does it take to evaluate the algorithm for n plus 1 data points? N plus 1 to the third power, right? And then you have to subtract them to calculate the difference. So what's the difference in time? It's n plus 1 to the third minus n to the third. And who remembers your algebra? So what is n plus 1 to the third minus n to the third? Not quite. That's close, but not quite though. Yep. So if you cube that all the way out, you'll get, notice n plus 1 cubed is actually n cubed plus 3n squared plus 3n plus 1 minus, and then the rest of it is just n cubed. So if you subtract those from each other, what's left? You already said it, I think, right? 3n squared plus 3n plus 1, right? So if you cancel n cubed and then minus n cubed, that's how many more seconds it will take to do n plus 1 data points. By the way, there's a quick I want to digress a little bit. There's a really mysterious thing that I want you to think about a little bit in your minds. So it's a very important problem in computer science. Like if you ever played a game or whatever else like that, it happens all the time. How do you calculate if you have points just in a game or like in the room? How do you calculate which 2 points out of all the points are the closest to each other? So like if you're flying in a game or whatever like that, how does the game know which thing in the whole room you're closest to at that moment? So like let me just give you a hypothetical example. So I'm going to go to a new page in Moodle because this is related to that same formula that we just used. Let's say if you have a list of points like this. Point number 1 is like the point 1, 1. So let's say your game is 2-dimensional. The point 1, 1 is like right there. Point 2 is just some other random point like -5, 3. -5 and then 3. So make sure you're watching your screens. Then point 3 is like another point like let's say 2, 4, somewhere out there. And then you'd have a big list of points. So out of that whole list of points, how do you tell which 2 points are the closest, like about to hit each other? Like how does the game keep track of that? Because you basically have a big list of points and you want to know which 2 points are closest together. So like, for example, is it going to be like this point right here and this point right here? Maybe they're the closest. Or maybe it could be like that point right there and that point right there. They're the closest. So how do you calculate which 2 points are closest? So what can you do? Can anybody visualize a procedure that could calculate which points are closest? What?
Calculate points together.
The distance between them together? Yeah, so you could do something like this. So you could say 4i equals 1 to n, and then you could calculate the distance between point I and point, well, in order to calculate the distance between the point you're on to the other points, you'd have to have another loop. See that? So you'd have to have an inner loop. For I equals 1 to n, and then you'd have to say for j equals 1 to n. Then you'd have to say, calculate the distance between point I and point j, right? And then you'd say something like this. You'd say if so you'd begin the code by saying like this. You'd say like minimum distance equals infinity, right? So you start with the minimum value of infinity. And then you'd say if the distance between point I and point j is less than the minimum distance that you have already found, then you'd set the minimum distance equal to that distance, equals to this distance. And then you'd stop your code. So basically when you ran that code, you'd find the smallest possible distance between any point versus any other point. So when that code ended, you'd be guaranteed that the value of this minimum distance would equal the distance between the closest pair of points. You can't see it on the screen, but you can see it on your small screen. So how many steps would that code take to run? The code that I just mentioned to you to calculate the closest 2 points together in a game or in the real world or whatever like that.
Yeah, it runs twice.
It'd have to run twice through all endpoints, and so it'd have to for every single for every level of this loop would have to run n times, right? So this loop would have to run n times, and for every one of those times, this loop would have to run n times. So it'd be n times n. So that would be an n squared algorithm. So the mysterious thing is they never even knew for sure for a long time whether this was true or not. But finally, somebody invented another set of computer code or another algorithm that could calculate the closest distance between 2 points without having to run through all endpoints and all other endpoints. They were able to shorten this algorithm down so that it didn't take n times n steps. It only took n log n steps to do it, which is basically incredible. So I want you to ponder for a while because it'll be good for your brain. Try to think of how you could calculate the closest 2 points to each other without actually having to check between every possible pair of point compared to every other possible point. And think about if there's possibly a way to do that or not. Well, anyway, let's go back to this other page. But that's a very important problem to think about. It will help you if you can figure out a way of doing it. It'll help you get really smart. So now let's go to this next one. So the next one is n squared. How much time longer does it take to run an n squared algorithm on an input level of n plus 1? So by the way, this answer right here, that answer actually belongs up in there. So let's scoot this one down here. So let's put the answers to n squared down on that level. So how many steps does it take to run an n squared algorithm on an input level of n plus 1? What do you have to do to it, LaShawn? Plug in n plus 1, right? So what do you get if you take n squared and plug in n plus 1 for the value of n? What if you take n squared and plug n plus 1 inside of the value of n? What do you get? You get n plus 1 squared, right? And what is n plus 1 squared? Can anybody tell me what n plus 1 squared is?
Parentheses n plus 1 squared minus n squared.
Yeah, so the difference between them is n plus 1 squared and minus n squared. But what is n plus 1 squared, though? Can you evaluate that? What is n plus 1 squared? If you multiply that together, what do you get? Yep, n squared plus 2n plus 1. So the difference in time it takes is n squared plus 2n plus 1 minus n squared. That's how much the time it takes to do the longer one minus the shorter one. What happens when you subtract the n squareds from each other?
You get 2n equals 1.
Correct. Exactly. Now let's go ahead to do, let's go ahead and do 3n, let's see. So how much time does it take to run an algorithm that takes 3 to the n steps if you do it on an input level of n plus 1? What do you have to do? Does anybody remember? You have to plug in n plus 1 to the value of n. So what is that? 3 to the power of n plus 1, right? So that's the time it takes to do n plus 1 steps. And then when you're doing something that's an exponential function, it's hard to express it as a subtraction. It's better to express it as how many times longer it takes. So like instead of saying this takes 1 second longer, it's better to say it takes twice as long or it takes 3 times as long. So this time, instead of expressing the difference between the times as 3n plus 1 minus 3 to the n, instead of that, we're going to actually do it as 3 to the n plus 1 divided by 3 to the n. So what is 3 to the n plus 1 divided by 3 to the n? So we're not going to do that one. We're going to do that one. What's 3 to the n plus 1 divided by 3 to the n?
2.
Well, the 3 to the n cancels the nth power of 3, right? And then we're left with 3 to the 1th power. What's 3 to the 1th power? 3. So now that 3 does not mean it takes 3 more seconds. This is a ratio. So it does not mean 3 more seconds. It means 3 times longer. So it takes 3 times longer to do the code if you only add 1 more data value to it. So imagine you had an algorithm that if you put 1 more data point into it, that it would take 3 times longer. That would make a huge difference, right? So let's look at the next one, 3 to the n squared. So how much time does it take to run the algorithm on n plus 1 data points if it has a speed of 3 to the n squared? Sorry, I need to erase some of these lines. There we go. How much time would it take? It'd take 3 to the power of n plus 1 squared, right? So by the way, this page is getting a little bit full of information. So let me go ahead and, is it okay if I erase? Let me just go to a new page actually. So I'll rewrite this on a new page. So 3 to the n squared is what it was, right? I already forgot what it was. Hold on. Let me go back and look. Although I changed it, so 3 to the n squared. Yep. So how many steps did that take to run on n plus 1 data points? All you do is plug in n plus 1 for the value of n. So I expect you all to be able to do that part. Any questions about that? Now, how much longer does it take to run that code on 1 more data point? How many times longer does it take? How do you calculate that? You take the time it takes to run it on n plus 1 data points divided by the time it takes to run the algorithm on n data points. That gives you how much times longer it takes, right? Like if it takes 800 seconds on the top and 400 seconds on the bottom, that would result in 2. So it'd take 2 times longer, right? But we have to figure this out because this is going to be a complicated expression. So remember, you told me n plus 1 squared equals 2n. No, it equals n squared plus 2n plus 1, right? So Zoe said n plus 1 squared is equal to n squared plus 2n plus 1. And you're right about that. So that's what it would be, is 3 to the power of n squared plus 2n plus 1 divided by 3 to the power of n squared. What can you do with powers, by the way? Let me ask you a quick question. What if this, instead of that, what if this was like 3 to the power of 5 plus 2 plus 1 divided by 3 to the power of 5? What could you do in the case of if it was like 3 to the power of 5 plus 2 plus 1 divided by 3 to the power of 5? Does anybody know, does anybody remember from algebra what we can do? Yes, well, except assuming we couldn't add them though, because notice that we can't actually add these exponents together on the top of that one because they're not like terms. So we can't add the n squared plus 2n plus 1. So if adding them together isn't an option, then what could we do? You can always subtract exponents from the bottom, right?
Yeah.
So we could take all 5 of these, cancel them out, and subtract 5 from the top, right? And then we'd have 0 3s left in the bottom, and we'd have 2 plus 1 powers in the top, right? We're going to do the same thing with this. We're going to cancel out the 3 to the n squared in the bottom, cancel out subtract the power of n squared from the top. We'd be left with 3 to the power of 2n plus 1, like that. So that's how many times longer it would take to do it. Perfect. Let's see. Does anybody know of an algorithm that might take that many times longer to do?
Where you add to the third power.
Or something that's like that like takes a whole lot longer to do one more data point? Well, that's okay. Let's go ahead to the next one then. The next one was n factorial. Oops. Well, the next one was n factorial. So if it takes n factorial steps to run an algorithm, then how many steps does it take to run the algorithm on n plus 1 data points? It would take it n plus 1 steps, right? And how much longer would it take to do that than before? So once again, we're going to express this as a ratio. So we're going to take the time it takes to run to do the data on the larger set divided by the time it takes to do the data of the smaller set. So it's going to be n plus 1 divided by n. What is n plus 1 divided by n? Well, first remember what what does the factorial represent? A factorial represents n times, and then it lowers down all the way until you get down to the number 1, right? So like n times, like for example, if n is 10, n factorial, if it's 10 factorial, would be 10 times 9 times 8 times 7 times 6. So it'd be like 10 times 1 less than 10, and then keep on going down until you got times 1, right? N plus 1 factorial would represent 11 times 10 times et cetera. So it'd be 1 more than n, and then it'd be times n, and then it'd be times n minus 1, and then it'd go all the way down until you got times 1. So n plus 1 factorial represents n plus 1 times n minus 1 all the way down to 1. And n factorial represents n times n minus 1 all the way down to 1. Can anybody see any common factors? Can anybody see any common factors? And then 1, and then also n as well. So the only thing that'd be left is n plus 1. So if you have an algorithm that has an n factorial is the time it takes, then that means when you put in one more data point into the algorithm, then the overall time it takes is n plus 1 times as long, n plus 1 times as long to finish the algorithm as the amount of time it took before. Does that make sense? Perfect. Okay, great. So we're finished with that. Now let's learn about something really, really, really important and super cool. So any questions about that? So basically we figured out there's 2 ways to compare the time of an algorithm when you apply it to a data set. You can compare the speed of it by doing the speed it takes on n plus 1 steps minus the speed it takes on n steps. Or you can also compare it by taking the time it takes for n plus 1 steps divided by the time that it takes for n steps. Now we're going to learn something else right now called modular arithmetic. Modular arithmetic. So first of all, we're going to learn about something called the divides relation. So you've heard about this in the real world a lot of times, but we're now going to use this basically common sense idea in a, hold on, where is a napkin? That's right. Okay, so we're going to use this common sense idea just in a mathematical definition. So does 2 divide into 4?
Yeah.
I'm just going to say, does 2 go into 4? What do you think? Does anybody think 2? Raise your hand if you think 2 goes into 4. Okay, perfect. Are you guys paying attention? Do you think 2 goes into 4? Okay, so most of you think 2 goes into 4. So the answer is yes, it does. So the way we're going to write this mathematically is like this. 2 goes into 4. That's called divides into 4. That line right there means divides into, like that. 2 divides into 4. So let me ask you this. I'm going to write down a statement and you tell me which one's true. Is the first statement true that I wrote down, or is the second statement true? First. So that one's true, that one's false. So if you want to express that something does not go into something, you do a line through that, and then that makes it true. So 5 does not divide into 6. So that's called the division with a not, with like a not equals to sign. Just like if you say not equals, you draw a line through the equals. The not divides into means that. So 3 does divide into 6 and 5 does not divide into 6. Now, once we know the divides relation, now we're going to talk about the modular relationship. So this is going to be a little bit confusing though. So how many times does 3 go into 7? That's the first question we have to answer. How many times does 3 go into 7? Question mark. Twice. So there's that. Now that 2 is called the quotient. Quoti quotient. And then, but what's the remainder though?
1.
Yeah, the 1, and that's called the remainder, right? Now we're interested in that remainder. So think about a clock. If you had a clock that had only 3 hours on it, 1, 2, and 3, 1 o'clock, 2 o'clock, 3 o'clock. If you counted 7 hours of time on that clock, where would you be? So if you started at the beginning and you went to like 1, 2, 3, 4, 5, 6, 7, what hour would you be on after 7 hours? You'd be at the 1 o'clock hour, right? So in 7 hours, you'd be at the 1 o'clock. 1 o'clock, right? So what we say is that 7 mod 3 equals 1. So the word mod means the remainder when divided by. So the remainder when 7 is divided by 3 equals 1. Let me give you a couple more before we end class. So what is 14 mod 5? What's the remainder of 14 when divided by 5?
2 to the remainder of 4.
Well, you don't worry about the 2, just what's the remainder?
4.
Right. And then what is 10 mod 5?
There's no remainder.
So it'd be 0, right? So what is 15 mod 5?
Still 0.
Still 0. What is 11 mod 5?
1.
What's 12 mod 5? What's 13 mod 5? Correct. So notice the values of mod 5, there's 5 values, but it doesn't include 5 though. It can either be 0, 1, 2, 3, or 4. It can also be 4, but it can never be 5 because if something mod 5 was 5, that means 5 would go into it, and so it would actually have a remainder of 0. So you can never get the actual value of the modular of what you're dividing by when you get the output of a mod, because it gives a remainder. So you can never have a remainder that's the same as the number you're dividing by. So that's pretty much all there is for today, and we're going to talk about, next time we're going to talk more about how modular arithmetic works. And this is actually what encryption is based on. Like if you send data through the internet and like encrypted data with like secure certificates and things, that's actually based on modular arithmetic. So we can look forward to an exciting class next time. We might not get that far next time, of course, but we'll slowly learn more about it. Good job, everybody.